video, I want to take a little bit of what we did in discussion of how we apply energy methods to translation and to fixed axis rotation, and what those look like when they're put together to form the basis of general planar motion. So recall again that general planar motion basically means that we have a rigid body, and that rigid body is at the same time undergoing some translation, so we'll give it a velocity of the center of gravity g, and it's undergoing some rotation. We'll give it a angular velocity omega about g, but of course realizing that it doesn't necessarily need to be rotating about g. It can be rotating about any other point or undergoing any type of translation at the same time, which muddies the waters a little bit. But that's the basis of general planar motion, is that we both have translation and fixed axis rotation. So one way to look at this from an energy standpoint is that I can write an energy equation, in which case I take into account both the fact that its center of gravity is translating and it has an energy associated with it of 1/2 mvg squared, and at the same time it's rotating, and as such I can include that rotational energy in there as well. So really all we're doing is taking these two things, the energy of each type of motion, and sticking them together. One thing that's a little bit different from when we look at, for example, fixed axis rotation about a non-center of gravity axis is that because we have this translation happening at the same time, we can no longer say that Vg is necessarily equal to r omega, right? Previously we said that because we were talking specifically about fixed axis rotation, but if the body itself is translating through space, then this may not hold depending on the given situation. So it's a little bit of a simplification that we can no longer make. However, there is one circumstance in which we can still get a simple looking equation like we saw for fixed axis rotation, and that is through the use of instantaneous centers. So recall when we talked about instantaneous centers that an instantaneous center, for example, I'm just going to make up a spot, maybe this point right here. The location of the instantaneous center is defined such that at that instant in time, all of the motion that's undergoing with the rigid body can be approximated as fixed axis rotation around the instantaneous center. So if we can locate that point, which we talked in a previous video about how to do that, then we can rewrite our energy equation using the principle of fixed axis rotation as 1/2 times the moment of inertia about the instantaneous center times the angular velocity squared. Now we have a simplified equation, realizing of course that the moment of inertia of the instantaneous center likely includes a parallel axis theorem term, which allows us to take some instantaneous some mass moment of inertia that we know and offset it to the location of the instantaneous center. So that really gives us the general ability to apply this one equation to many different scenarios, assuming we could find the instantaneous center. So it's really a powerful tool to be able to analyze that. From a work perspective, when we're talking about general planar motion, not too much changes. We can still input energy via work into the system or extract it out by applying a force over a translational distance, or by applying a torque over some angular change in position. So we still have methods for inputting or extracting energy from the system, and they don't really look a ton different when we're talking about general planar motion. So I'll leave it at that. Thanks.